This is the first video in the chapter about equilibrium. We're going to start from the beginning by talking about what equilibrium is and what it isn't. So we did a little bit of hand waving towards equilibrium a little bit earlier in this course when we talked about coffee in a mug in the vapor pressure chapter. So hopefully this picture looks familiar from a previous video. We said if we have liquid coffee in the cup, by the way, this is the coffee, in case it wasn't clear. This is the coffee, this is the lid. So if we have liquid coffee, we have molecules here at a variety of temperatures. Some of those have more kinetic energy than others, and they have enough kinetic energy to jump into the gas phase, and that process is called vaporization. And we said vapor pressure is created not just by vaporization, but by the dynamic equilibrium between vaporization and its reverse reaction, condensation. Some vapor particles cooling and reverting back into the liquid phase. So that was our very first equilibrium. So let's write it out officially here. Liquid to gas phase. And as we did before, we gave a name to this forward reaction. We called it vaporization. And now we're going to rename it, and we're just going to call it more generically the forward reaction, going from left to right. And we also named the reaction from gas to liquid. We called that condensation. And we can name that one the reverse reaction, meaning it moves from right to left as written. And so both of these processes are happening at the same time in the container, vaporization and condensation. So to represent that, we're going to give it a new kind of an arrow that looks like this. The top half is going to the right, and the bottom half is going to the left to represent the forward reaction and the reverse reaction, both happening at the same time. So now that we have a picture to talk about, let's dive into those words a little bit more. This is called the dynamic equilibrium. So dynamic means that both of the reactions are happening at the same time. So we're going to start to abbreviate here, forward and reverse reactions both happen simultaneously. At no point do the reactions stop. They might be progressing slowly, but they don't stop. They are both happening simultaneously because it is a dynamic equilibrium. Okay, and the other important part is the word equilibrium. Equilibrium means that the forward and reverse reaction rates are equal. There will be more to come on reaction rates in a future chapter on kinetics, but for now you'll have to take my word for it that these reaction rates are going to be equal at equilibrium. So emphasis on rates are going to be equal. So the rates are going to be the part that's equal, not the amounts of reactant and product or anything else. The amounts are going to vary, but when the reaction rates are going at the same amount, that's equilibrium. So now let's illustrate that with a graph of how these things change over time. So to prove that it is not the concentration, let's start with a picture of that. So my reaction was from liquid to gas. So let's say that we started with all reactant in our container. So at time 0, we're going to have a high concentration of the liquid in black. And we're going to have a concentration of 0 of our product, the gas. And what's going to happen is if I start with just liquid coffee in my container, some of it is eventually going to start vaporizing and some of it is going to be lost and turned into gas. So some of the liquid starts to disappear, and eventually it reaches a steady value. And the opposite happens for the gas. So at the beginning, there was only liquid coffee, there is no vapor. And then some of the liquid starts to jump into the vapor phase, and some vapor is formed, and a little bit more is formed, and a little bit more, and eventually it reaches some steady amounts. So a couple important points about this plot. The first one is about the value of the concentrations. We're going to start using this bracket to indicate concentrations. The concentrations reach constant values at equilibrium. Now remember, the reaction rates are the one that's equal. The concentrations are not equal. These lines are not in the same spot, but they do level off. They've reached a constant value. And so we can mark the equilibrium on this picture by marking where they level off. So I would say that's approximately here in the picture that I drew. So from here where they start to level off until the end of time, that is going to be the equilibrium portion of the graph. So you should be able to identify that. Okay, so now we've looked at the concentrations and observed they are not the same, but they are constant. We can also look at the rates of the forward and of the reverse reaction. So the forward reaction rate was the one that made these things, and it started out high because the forward reaction was in full blast when we only had reactant, and then as we started to make product, it started to slow down and it reached a constant value. So this is the forward rate over here, and the reverse rate started at 0 because there were no products, so the reverse reaction couldn't happen at the beginning. But once there were some products, some gas formed, then the reverse reaction could start to happen. So it began to happen, and it increased in rate until it matched the rate, that's hard to see, until it matched the rate of the forward reaction. So we don't know where this value is going to be. That's going to depend on what the actual rate is, but we do know that the numbers are going to be the same at equilibrium. So the forward rate equals the reverse rate at equilibrium, and hopefully this line is at approximately the same point. It's not awesome. I probably would have said it was like here, but ideally those graphs should match. They should have equilibrium marked at the same point. So now we know that equilibrium is about the rate of the forward and the reverse reaction matching each other. And in the next video, we will give a new numerical value called the equilibrium constant to help us explain where that equilibrium occurs.